This work presents a control framework for legged robots that leverages unstructured real-world animal motion data. Our approach not only learns individual motion skills from pre-recorded animal motion clips, but also develops a controller that responsively tracks user-specified velocity commands and adaptively switches gaits, replicating high-level behaviors observed in animals. Our framework is structured into 4 stages. To begin with, we transform animal motion data into a robot-compatible motion database. From a source animal motion sequence, we extract the base pose and limb vectors, and scale and transfer them to the target robot. However, simply scaling and transferring the motion feature trajectory introduces artifacts such as limb penetrations and contact foot slips, which may hinder successful motion imitation on the robot. To address these issues, we formulate and solve a constrained inverse kinematics problem that enforces limb and joint constraints, eliminating kinematic artifacts from the retarget motion. Additionally, we use model predictive control as an offline optimization tool to further refine the constrained IK solutions, taking into account the robot's system dynamics and physical constraints. We use this kino-dynamic motion retargeting strategy to convert animal motion data into a robot motion database that is kinematically and dynamically compatible with the target robot. In the next stage, we embed the state transitions from the retarget motion database into a latent space using a variational autoencoder. Leveraging this latent space, we train a motion synthesis policy using reinforcement learning to generate reference motions aligned with the user's velocity commands. This motion synthesis module preserves the stylistic quality of the original motion database and generates motions that are responsive to the user's velocity commands. Furthermore, it captures diverse gait patterns and smooth transitions based on the velocity commands. As a last step, the reference motions are executed by our motion tracking controller, trained with the motion synthesis module in the loop. In our experiments, our kino-dynamic motion retargeting enables reliable motion execution for a fast spinning motion by mitigating artifacts, while the baseline UVM method suffers from severe foot slips, making the policy less suitable for real-world deployment. For the dynamic gallop motion, the UVM retarget version results in poor tracking performance, while our method enables more accurate motion imitation by accounting for dynamic effects in the reference motion. In summary, the kino-dynamic motion retargeting method effectively transforms agile and expressive animal motions into robot-compatible trajectories, enabling consistent and accurate execution on hardware. Our control pipeline replicates animal-like adaptive gait switching in response to target velocity on the physically simulated Unitree Go 2. Finally, we deployed the full control pipeline on the robot hardware to enable responsive, real-time steering while preserving stylistic coherence with the motion database. With our pipeline, the Unitree Go 2 robot autonomously adapted its gait in response to changes in the user's joystick commands, exhibiting animal-like behavior as it freely navigated a grass field. Thank you for watching.